Hello all, welcome to the next and last of this term Go seminar. And today we have, dare I say, our own Hanka Řada talking about flip processes for permutations.
Hey everybody, I will tell you about my research with Jan Hladký from the Institute of Computer Science. We were investigating permutations, typically very large permutations. So for now, for better visibility, imagine that 10 is a really large number. And we always have some permutation, and then we do some process with it. The process is done in the way that we always sample a k-tuple of points from this permutation and do some local change on these points, and then return them to the original permutation. I will explain this in detail later. And via this process, we are changing the permutation in each step, and we can, for example, investigate how to which permutation the process converts, or so on. So what we do, we have the permutation, and in each step we sample, for example, a triplet of points. We look on which permutation these 3 points induce. So in this example, we had the points induce this permutation, and we reorder them. So we change this subpermutation to the increasing permutation, for example, and then we return these points on the appropriate indexes or the appropriate places in the original permutation. So we transplant the changed permutation into the original one. And with this process, we can, for example, sort permutation. Imagine that you have a row of kids and you want to sort them according to their height. But you can always touch only 3 kids at a time. Not only, but exactly 3 kids at a time. And you even do not know which of them, you cannot choose which of them you touch. So you always pick 3 and order them in the, like that they are in the increasing order of their heights, and then return them to the row on the places where they was, but these 3 can be changed. So, for example, now we take these 3 points and order them. Then we take these 3 points and reorder them, and so on and so on. And in this way, we sort the whole permutation like this. And eventually, we are getting closer and closer to the diagonal, to the sorted permutation. And from some time, it will happen more and more often that we touch 3 points that are already ordered. So we do nothing, we just put them there. And in this way, the process slows a lot. So after a lot of another steps, 20 or 50, we get the ordered permutation. So in this case, we did a process with such a rule. This rule says that if you sample 3 points and there are in one, and these 3 points induce some of this permutation, you always reorder them so they build an increasing permutation. Okay. We can have another processes with another rules. So for example, we could also sort permutations with a rule lazy sort. So in this case, you are lazy and you do changes only if they have a big impact. So you always sample 3 points, and if you see a decreasing permutation, and these 3 points, you reorder them so they constitute an increase in permutation. So if these 3 points were in some other permutation, then you do nothing. So, do you think that this process will also always converge to the diagonal, to the increase in permutation, or not? Yeah, it will not, because if, for example, if you start with this permutation, then in every step, it will look like this. Nothing new happens. So you can see that it really depends on how exactly the rule looks like. And in general, the rule can look like this. You do not need to know deterministically how you reorder the points, but you can, for example, in this case, you have to flip a coin, an unfair coin, and there is a 60% probability that if you sampled this permutation, you return this permutation, or 40% probability that you return this permutation. So, but always the rule is a stochastic matrix, so the probabilities count to 100%. And if I write it rigorously, then the rule is this stochastic matrix, and it's big as, and it says if you see one permutation, what are the probabilities, how you change it. So, and the process is this process. You always start with a large permutation, and in every step you sample a k-tuple of indices, and then you pick the permutation to which these 3 points are changed and transplanted into the original one on the given indices. And this is a discrete-time homogeneous Markov process. So how we investigate these processes? We do it via permutons, because if you take discrete structures, they are difficult to investigate. So we are looking on their limit objects, and limit objects for permutations are permutons. Permutons are limits of permutation sequences, and there are probability measures on a square which have uniform marginals. Why uniform marginals? Because if you have permutation and you have large permutation, there's and there's 3 points, there's 2 points, and then you know that if you count all the points that are in this sector, you have exactly q minus pi points of the permutation. And the same holds also for their values. Like, you know that exactly that exactly L minus M points has value between L and M and L. Okay. So these are permutons, and they were first introduced by these guys 13 years later. And we denote the set of our permutons with this symbol. So how connects the permutations and permutons? It's in the way that every permutation can be represented as a permuton. How we do it? Okay, so imagine that we have here some permutation. example, something like this. And now we divide the square into subsquares that are which range is exactly 1 over n, when n is the number of the points in the permutation. And instead of the points we are placed here squares, and the probability of the square is depends on the size of the square. So the permuton is this probability measure, and we can measure the distance between two permutons in two ways. The first is total variation distance, and it says that, and it is a distance, is this supremum from the differences of the values of the permutons on regions from the square. So you compare the two permutons and you take the biggest difference between them. And in the rectangular distance, you do the same, but you can use only rectangular regions to compare them. So you lost some information, and in some cases this can play a big role, but it's really important for the left convergence of the permutations.
So, sorry. So is the second one the one that we briefly call cut distance?
Yeah.
Okay.
Yeah, but for the permutons, there are some problems with it. Okay, so now I want to go to the convergence results. So before that, I have to introduce you to the concept of densities of subpermutations. Firstly, permutations. So a density of a of permutation tau as a subpermutation of a permutation P is the number of occurrences of tau in P divided by some number, by the number of how many k. In fact, it's the probability that if you take k points from the permutation P, then you get the permutation tau. And the same holds for the permutons. So the density of a permutation in a permuton is again the probability that if you choose randomly a k-tuple of points from these permutons, then the set of these points gives a permutation that induces the permutation omega. And now what means that if I say that a sequence of permutations converge to some permuton, then it means that the densities of every subpermutation of these permutations converge to the densities of the subpermutations in the permuton. And at the same time, we need to look at the length of the permutations goes to infinity. Yeah, because if it's not fulfilled, then we eventually get that the sequence of permutations is constant, or it has a constant subsequence. So it's not interesting. Okay. the limit object is not unique, but it's unique if we take it, but it can differ only on a set which has a Lebesgue measure equal to 0. So, and now there are the results about the convergences of the permutations. We have that not every permuton is a representation of a permutation, but at the same time, each permuton is a limit of a sequence of permutations. And vice versa, every sequence of permutations contains a subsequence that converges to some permuton. In fact, every sequence of permutations converges to a permuton if and only if it is a Cauchy sequence with respect to the square. To the rectangular norm. So how can look the process on permutons? So now we take an increasing permuton, and permuton that is a representation of an increasing permutation, and we want to do contrary to the sorting process, we do a reverse sorting process. In every step, we sample a k-tuple of points, and we put them into a decreasing order. And then the process on the permuton looks like this. Very similar to the process on the permutations. There's some scaling in the number of steps. And in every step, we get closer and closer to the anti-diagonal permuton. And now what was our research in this field? We showed that we can, we have functions for every k and every rule. It's important that the k and the rule are given at the beginning. Like we are working with one rule, and for that rule, we can find trajectories. Trajectories are functions of a permuton and a time, and then show how the permuton is evolved in a time with the process with the rule R. Okay, so if we find the trajectories, we can, for example, find whether the trajectory is cyclic, whether we can have whether this process is like that we eventually get to the beginning. Or we can investigate whether such processes exist. And what we've shown is that the transference theorem, which says that if we take a big permutation and we do the flip process with it, then after t steps of this process, with the rule R, we get close to the trajectory, to the permuton, which is given as the trajectory of the initial permuton, of the permuton representation of the initial permutation at time t. So that the trajectory is close to what the permutations do in the process. And how these trajectories are given? They are given via a velocity function. Velocity function is a derivative of the trajectory, and in fact it says how is the trajectory changing at the moment. So we have here the trajectory, and the velocity is the direction of the trajectory at the given time. We can compute them, and using them we can find the trajectories. Yeah, and why this is good, how we can use it. We can, for example, go back in time. We can look like, now we have this permuton and this process, but was there some permuton from which this was given by this process? Like, was there some permuton from which we could get to the permuton we have now using this process? We can also investigate whether the trajectories get periodic, if there are some fixed points of these trajectories. Or we can investigate the speed of the convergence of such trajectories. We already saw that the process with the rule sort was probably much faster than the process with the rule lazy sort, although it could look similar. It can converge to a similar permuton, but not in all cases. Okay, and all of this work is a counterpart to the similar work on graphons, as you already mentioned them. And because on the graphons, Garbe, Hladký, Šilekis, and Skerman investigated the flip processes on graphons and find similar results. But between their results and ours, there are significant differences because these two settings use different Banach spaces. The graphons use are spaces of two variable functions equipped with the L infinity norm, while the permutons are measurements on a square equipped with the total variation norm. And there are some very different details. Okay, so that's all. I think for
questions. So are there any rules for which the trajectories are cyclic?
We do not know it. Like we are working on the theory of these processes, and they are much more complicated than because in the theory there are problems that are not in the graphon settings, so it's not so easy to count them.
I didn't get how from a process, what do you call it? Or sorry, so there was one thing was the function where you have a permuton times something from the unit interval gives you permuton, right? What is this called? Sorry.
Trajectory.
Trajectory. Like, okay, so when you and the processes are those given by the rules.
Yeah.
So when you start from a process, how do you get to trajectory?
Yeah.
Because one of them is continuous, the other is really not. Or is it because you're using the probabilistic?
Yeah. It's like that in every step of the process. Like if I have a permuton and I have the rule, then I can compute how it will be probably changed now this time.
In one step.
In one step.
Yeah.
Like or in some, I don't know, epsilon n steps, because we are looking for, because one step is too small compared to the continuous, compared to really big permutations. We are looking on infinitesimally small number of steps, and we are looking how it's probable that it will be changed. That is given by the rule, because you know what are the probabilities that if you sample, for example, 3 points, then you know the probability that you will get, for example, this this permutation on and in the given sector of the permuton. Okay, and if you know the probability that the 3 sampled points will be this, if you know the probability that the 3 points you sampled induce this permutation, then you know the probability what will you give back, because it's given by the rule. So, for example, you know that you will give back this permutation, and using this you can compute how probable it is that the permuton will get bigger measure, for example, here. That it will be more probable that in the new permuton of epsilon n will be more points here, for example, or on any other function.
Yeah, that is still quite discrete. So where do I use the epsilon?
Yeah, because in fact, in the permuton, if you change the position of 3 points, then the permuton doesn't change at all. So you have to take epsilon endpoints if you want to register the change. In the permuton setting, the thing that you have, in fact, you take the epsilon and points in the permutation, but you have to, for the permuton, you do the process for the time epsilon.
Good. So, some other questions?
I mean, there was one, there's in constructing the the trajectories. There is some kind of differentiability, some kind of smoothness conditions, and how are they satisfied?
One more time, please.
So when you define, I mean, there was at some point there's a formula for the trajectory in terms of some derivatives. Yeah. So how do you know these derivatives exist? Is that, sorry, I've forgotten the definition of Martin. I mean, how do you know that there's this enough differentiability?
Yeah, we like this. We are doing this.
Okay.
The derivation exists.
It exists.
Yeah, and they are satisfying the conditions, like for example that there are signed measures with the trivial marginals. In fact, if you are doing the derivative of the trajectory, then you are evolving from the permuton. Like if you then you can get something else than a permuton, because, for example, in fact, you can get negative measure somewhere, but yeah, there is a way to derive it.
Okay. Okay, thanks.
Okay. Further questions?
If not, then let's thank the speaker again.